Welcome back. We're writing Little Man Computer in C++, and we're now well on the way to getting our little man parsing an instruction. So we shall continue progress in that direction. But first, just continue chipping away at the problematic global variables in the tests. I think I might just move us one step closer by wrapping all of this in a class and see what that gets us. Just check all of the tests pass. They do, that's fine. So we can probably do this relatively easily by going to the top here and just moving up this test struct out of the way, and then just create a class around all of this lot called test fixture. And that will have to not be static anymore. And these are just private members, private fields now. And at the end here, we will close that off and have this also wants to not be public, and then we should perhaps just be able to then create a public run method. In fact, let's do it this way. A public run method that just encapsulates. I've probably got some interesting issues with this, but we'll sort that for now. We'll put that in there, just as is. And that should be okay. And then we can change this all to be test fixture, and then return fixture.run in principle. And let's see how many horrible errors we've introduced doing that. So there's a capture problem here, so we'll need to do something like that. No, we won't. That's not quite. Is that the search? Yeah. So that's fine. So what was the issue here? If we do that, it does strange things. I wonder if that's not catching both sides. It's a little bit, can we be more precise? What happens if we do this? Oh dear, that's not doing what we want at all, is it? Or is it? No. So it looks like there's some sort of some issue here. with that. Let's just now wonder why that doesn't work. Let's escape these and see what happens. That's a bit bizarre. Do I have to escape them on both sides? No. So it is finding let's see which part it is. Okay, so it's capturing. Okay, that's capturing the right thing. That's a good start. So now that works. That doesn't work, so yeah, better. That looks more like it, doesn't it? How many errors have we got now? We haven't terminated our class. That's a nice simple one. That's built. Interesting. Does it all pass? Yes, it does. Excellent. That was slightly more messing around than I was expecting, but that's fine. And then we'll need to just indent things a little bit. There we go. So there's our assertion, computer tests, little man tests, and a run method. Excellent. Let's just check that indentation didn't break anything. Can't imagine it would have done. I think that probably does the job. Excellent. Right, let's just commit that. Wrap label tests in a fixture class. Lovely. And we can get on with the task at hand. So somewhere up here is our tests. So we've got as far as the load instruction. And the next thing we're probably going to do, so we've done input and output, we've done load and store, and we might as well do the add and subtract tests next. So little man interpreting add instruction results in accumulator being incremented by content of memory. That's probably okay for now. Probably capturing a little bit too much scope there, but maybe not. Set equal and some random numbers here. So we'll do 1 plus 2. It's nice and easy. Check that the accumulator is correctly modified. We'll create a computer, just skipping a few of the steps of running the compiler when we know what's going to happen already. And that fails sensibly. We then need our man to run, so we'll need a little man. thinking about it. And that seems to do something sensible. So now we can write our program, or we can set the state. So we want to start with an accumulator of 1 and a little program which is the add instruction, which is 1. 1, 2, 3 sounds fine. And then halt the program, but also set memory address 23 to the value 2, which should give us the appropriate result. And the test should still fail. And it does. So now we can edit our little man's behavior. And at some point we want to reorder those, but that's a separate stage. Let's continue the previous mechanism of extending this, so that's 500. Feels like some refactoring of this is soon going to be possible. And then we have computer add, and 23 was our memory address, wasn't it? And hopefully that will pass the test. And it does. And we can do some sensible refactoring here. We can make that address. And I think perhaps we want to wait for one more instruction type to be introduced here, just so we have 3 examples of this structure before we move on and refactor it. So that's fine. Let's continue with the subtract instruction. Should be relatively straightforward. Little man interpreting subtract instruction results in accumulator being decremented by content of memory. Again, somewhat verbose naming of tests here, and at some point we might address that. So assert equal subtract. Let's go with 12, which we'll come up with some way of getting to in a moment. Accumulator, and we need a computer. That should compile okay. Oh, it says no write since last test. That's a useful warning. Let's just make sure that's doing the right thing. We shall see now that the test fails properly. Then we want to run the man, and then we need a man. Computer, like so. That should also fail, but with a slightly different value in the accumulator. And it does. And then we can write our little program. So we'll start by putting a value in the accumulator of 37, and then we can write our little program into memory address. I think it's so we've got 200 to subtract, so 2, 3, 4. Computer memory 1 equals 0 to terminate the program, and then memory address 34 will be the value 25, which should correctly leave us with 12, but the test should fail as we've not implemented the subtract yet. That looks sensible, and we can now make that pass by, these are the 100s. Instruction is less than or equal to 199, so that should keep that working. And then we can put our else computer dot subtract. And I'm going to use address here because that is the simplest way of making the test pass, because I can't remember which address we'd used in the test. And we've got a few too many characters in our less than or equal sign. So hopefully that makes the test pass. And indeed it does. And we've got a lot of structural duplication here in the checking for which instruction type we have. So the commonality here is the hundreds. So I wonder if we can do some mechanism of getting that value there. So these are all integers, so we can do potentially do some sort of integer division by 100. Let us give that a go. So instruction type equals instruction divided by 100. And then here we can possibly do instruction type equals 3 and see if that works. Waiting with bated breath. Yes, it does. That's very nice. And so we'll do the same on these. Instruction type equals 5. And here instruction type equals 1. Like so. That's removed quite a bit of, well, simplified the code quite considerably. And that all still passes, which is nice. I quite like to reorder the numbering here, so that it's a little bit cleaner. So we can do that if temporarily we'll make that an else if, and then take that one, put it there, and then take those and put them there. Let's give ourselves a little bit of space here. So that's now at least in numerical order. These are fine as their specific instruction values, so I think I'm happy with that. And then over time we'll gradually rearrange these and insert them in the appropriate places. Let's just check the tests still pass. I don't, because I've left everything as else ifs. And the rain has now started very heavily outside, as you may be able to hear, and that looks good to me. So I think we will commit that. That's good. That's some refactoring of things. Yeah, so git commit. We add little man interpretation of add and subtract instructions. Excellent. And we shall leave it there.